And so you tell yourself this morning, I know, let's teach it the time. Like, it's so bright. Here's 6 years of life, my third year. So it would be, yeah, out there, yeah, there's a drum. Easy. Oh, have to say, yeah. Actually, I'm teaching things like, it's the team. Long enough, it's long as possible. So my cousin's kids are in one street from the town. And if you go, if you're like, so obviously to the thing, get their cousins with okay, you know what I mean? Yeah. Yeah, but you go across, that's when it's like, that's why it's got it right here. Fantastic. This is very start to embarrass her properly. And in my first name is girl. Helen Cajun requested privilege. Her circumstance. And my grandmother came here to say accident, and my grandfather came from a local apartment in Jesus. They both had been here. They didn't. They were from the same area, so like no, Jesus, Dina, we came in. His charity is automation. Singer songwriter coffee table. That's great. Goes down, go and roll it. No, like he wants. So he was challenging this inside. He was using the right still very small. Yeah, I saw this yesterday. Well, the other night was the full moon coming out, cloud, and it wasn't feeling embarrassed anymore. And I've got 14 years down. Yeah, the minus they still have 8. It's got the doctor, yeah, and the other traces, how they should have tried. Right on the website. Listen. She went to 5 percentage. Yeah, each of the has conditions. What's that generation where I'm my third cousin that I met. My grandmother's uncle. Yeah, they had nice presentations. And she takes my stock. My grandmother was living in connection with them. So I can. Yeah, just to make it like we just like yeah. So there were something. I think conversations were also checks the okay, people years. Without my neighbors out, I have to be here for it's trying to be into the list. What's the treasure thing? Okay, how are we doing? We've got a minute or so to get it started, I guess, because Dr. Yancey's are all. We can work see the little rain, but that's the one thing I was great about the meeting. The campfire like that. And then Thursday around the campfire, but it was rain, so we set up my iPad and we and watch Hitchcock's for stone. That was fun. Yeah, have a beer, some snacks and stuff, and it's fine.
Well, that little pond there, it's from the dam side. It was so much fun when it was a clear night just to set up on there and just watch the milky rain. Yeah, we did have one clear nights. But we had the moon popped up. Yeah, we didn't have a few stars. Someone would say, I was also each other. Oh, great trip. We got the box of made and painted, huh? Yeah, that stuff. What's like actually? It's easy to mix it with water and slap it on there. Within about 10 or 15 minutes, if the color completely changes to that on the weather book. Yeah, okay, good. And guaranteed it's safe and non-toxic. Okay, safer than so we'll show that. Good. When bag came with powder and I retired there, you know, not for wow, he's been up to make 5 gallons of stuff. We still have one. I help the team. I mean, you all need 5 to do it. Make sure we got only 5 minutes, right? Because that's what's going to be getting split. But you had it. So it's nice for you. But give another minute, 7:30. Okay. So I did my bit to get people and I put the Zoom link and everything on the Facebook page, and I sent it to DAS, DAA, and CAS. Okay. And yeah, so this is TBX movie. Well, it wasn't really very television, but yeah, thanks for the 30. She would have seen originally I was not going to work your ways. Yes, Richard stuff. We got to work. Somebody called her back to the switch. She had to give a deposition. Yes, I can say how we're start. Okay. I see Dr. Hanson's on. So okay.
I can hear you. It's a little garbled, I have to say.
Oh, we were talking quietly. Okay, everybody, welcome to our final meeting for the academic year. Glad to see we have some new faces and lots of old familiar faces, and yeah, yours too. Speaking of which, would you come front and center, please? What did I do? You'll see. It's not about that picture you have in the post office.
No, yeah.
Come on up here, please.
Another.
Or participating in public outreach at the Night Sky Network, you get a certificate. It's really cool.
Oh, that's
looking. This is one of the best ones in that.
Oh, that's great.
So congratulations and thank you again for helping us show the public the Night Sky. It's always great. In any event, I hope that everybody's excited as I am about this change in the weather. It really does feel nice, doesn't it? It's nice to see at night that it's not raining, cold, or both. And those of us that are itching to get our telescopes out and actually catch some photons are getting excited, as we hope all of you are. And in that vein, I would like to remind everybody that this coming Friday, I believe.
Yep, and I'll cover that. I have a brief slide or two Mike gave me.
Anybody that's telescope has been gathering dust in the corner. It's time to get the feather duster out, dust it off, and we'll see out at BRC. Excuse me, Red Clay Alliance. I'll get used to that one.
Mhm.
In any event, we have an exciting program tonight. And first of all, I'd like to turn it over to our probably one of the busiest members we've ever had, Don Knapp, who will
Ex-observing chair.
the chair emeritus. Chair emeritus. I like that title, don't you? Who will tell us a little bit about what's up for the month and some things coming up. And then we'll take it from there.
I'm just going to spend a moment on upcoming events. Mike sent me this. This is through September. And I'm going to talk about Brainerd and Red Clay separately. But Saturday the 20th, Hoops Park in Westchester. That's always a fun event. We get good turnout if the weather's good. And then Bailey Battlefield is a Malvern Arts Walk for when the moon is full, which I think you came from, right? You met. Yeah. So fortunately, you didn't have much of a view last Friday because it was cloudy. Cheslin, I'm gonna spend more time on in a moment. I'll skip that for now. In August, there's Battle of the Clouds, September, Hoops Park again, and in September, Star Farm, which is a great site to observe. The BRC events. If I can get this out of here. There we go. The BRC events, this Friday, as Dave said, and then we have one in June, July, August, September. We have them from there on, but Brandywine and Red Clay has not set their schedule yet, so they haven't given us approval yet. York County Star Party is only an hour drive from here. It's a nice event. There's one in June and one in September. I think we plan to go in September, that one. Green Bank in June, which is an amazing, amazing event. Barb and I are going to that in June down at the world's largest fully steerable radio telescope in the world. And we have 2 camping trips planned if the weather cooperates. So I'm going to stop that share. And I'm going to go to another one quickly.
Don, did you mention the solar event on June 30th?
I didn't. That's pretty much just something that it's being handled only by what's his name, Roger last name.
Roger Kennedy, yeah.
Roger Kennedy. He's handling that on his own. That's really not a club event. So those of you who have been with us a while know about Friday Night Lights. This is a I want my slideshow light up. Let me stop this share. Start again. Try that again. Back to Zoom. Share screen. Okay, there we go. All right. So Friday Night Lights is a Natural Lands Trust fundraiser. It is June 14th. And these slides came from Fred DeLuca. He was a member of our club years ago. He's the DIS member now. I think he's also a Chestnut member. He asked me to cover this to drum up some participants. So Fred coordinates this for DVAA, our club, CAS, and DAS. Okay, all the local clubs in the area. So I'll be sending this out by email, and you can respond to Fred directly. We can bring guests, which we've done before. We can bring up to 2. It's an amazing event. There are probably 700 people come to this event. It's actually a concert, fundraising concert, but we have telescopes set up in the back, and you'll see that. So sunset is 8:30, so we can actually start even with solar observing. There'll be Mars. I guess, is Venus gone by then already? Seems like Venus would be up. It's gone already. So after the event ends at 10, people can stay if they want, if the sky is good. But from previous years, there are still some COVID precautions. They will, it could be up to 700 people. So they'll hand out masks if you choose to use them. You could bring 2 guests with you, and telescope top of the hill just like last year. There'll be trash cans, recycling. They used to get free beer, but they don't anymore. They give you 2 tickets. Now they stopped doing that. So, but you can buy beer, food, wine. Okay, it's an amazing event, really. Again, Fred is the guy that's coordinating all. And I'll send this out by email too. But there's craft beer, there's wine, there's food trucks, and you don't need to buy a ticket. If you're an astronomer, you do not need to buy a ticket. If you have more than 2 guests, they need to buy tickets. But astronomers do not need to buy tickets. And it's not cheap. It's like $55 for walk-in. So they're gonna have 2 bands. So here's some previous events. Farm, I've been to most of them, not all of them. But we are set up behind the stage, and it's just filled with people. That's the astronomy section. And then during the shows or during the break, people come up and look through scopes. That was when we sit up along the road. That we don't sit up there anymore. But there is a really good view of the event. So yeah, 700 people, and it usually sells out. So Friday, July 14th, it's a lot of fun. You almost end up being hoarse by the end of the night because so many people come through the lines to the telescope. So okay. I have one more thing. I'm not gonna do the whole thing, but I do want to show you one slide that I can't resist showing you because Kathy's here. And she discovered this. So I'll just go super quick. I'm actually giving this presentation next Tuesday to the Global Star Party, which is an online astronomy event that actually has thousands of people attend online from Explore Scientific. So three leaps of gazelle, we'll spend a minute. So asterism is not, the Big Dipper is part of Ursa Major, okay? So it's an asterism, not a constellation, just like the sickle in Leo. So there's the Big Dipper part of Ursa Major. And there is the sickle, which a lot of young people don't know what a sickle is. I used to use it to chop weeds at my parents' house. Okay, people call it the backward question mark. So again, I won't spend the time because Dr. Hansen's already on here, but you know, the shapes in the skies are something that humans have always thought about and dreamed up. It's the way they would tell stories and pass it on to other generations. So you know, the night sky was beautiful, so they would see these patterns. It's a natural thing for the brain to see patterns. Okay, so the sky would become a storybook. The Astronomical League actually has an observing program just for asterisms. I know Frank Angelini has gotten this one. So there's you have to get 100 out of 112 on their list. So this is Buotes, the herdsman, but Kathy, you can make them for your own. Here's one Kathy made up. This is the same stars as the Buotes, but it's the martini glass. Okay. So here's one you can see tonight. So if you go out, look above Leo or Big Dipper, and see these three sets of stars. Okay, these are what's called the three leaps of the gazelle. Okay, and you could even see them in ancient diagrams of the sky. The three leaps of the gazelle. So you can go out tonight and see this. Okay, and let's go back to the 13th century. A creature was gazing among the back of the Leo Minor, which in some points was actually part of Leo's constellation. And the Leo switched his tail and the gazelle bounced across the sky. That's what the three leaps of the gazelle are. Those three pairs of stars. Okay, left behind the glowing tracks in the sky. And yeah, just to the left of rear Leo was used to be considered the lion's tail. We now call it Coma Berenices. And the stars aren't related. They just happen to be lined up for us to enjoy them. One of the stars is actually a red giant star. It's like 70 times wider than the sun. So, and that would be this. That's a red giant star, 70 times larger than our sun. So, so I just wanted to get that in because Kathy's here and she's the one that dreamed up the martini glass. Okay, so Bruce, you can introduce our presenter.
So everyone listening, Bruce and Jerry, I'm the program chair, and Dave mentioned this is our last meeting until September. So from September until February, our program is full, in terms of speakers, whatnot. But beyond that, it's still open. So as I always kind of make a plea to people, if there's topics you want to hear presented on, or even particular individuals you'd like to hear talk from, let me know. My number is in all of the mailings. You know, when I send out these announcements, just get in touch with me. I'll do my best to try to bring in the appropriate people. And obviously, ever since COVID, we're not limited by geography, and Dr. Hansen's good examples. We've been Tucson, we've had speakers from Italy, and it's all over the place. So the world is our oyster here. So just let me know, and I'll happily bring in speakers. Also want to make one other announcement. I think everyone is aware we started this year Chester County Astronomical has decided a scholarship, 2 scholarships to be given to Westchester University students that have an interest in astronomy, Earth, planetary science. And I found out today the awardees have been selected by the committee, and they'll be announced at our September meeting, and in all likelihood they'll meet at our September meeting. We'll introduce them. They'll probably even go into observations on periodical. So anyway, I think it's a successful first year with the scholarship, and apparently the 2 awardees are very, very good. All right, so for tonight, I'm really pleased to introduce Dr. Candace Hansen-Koharczyk, who is at the Planetary Institute in Tucson. And, we've had a lot of really good speakers. Okay. Dr. Hansen is a classic, I guess you would say. I mean, when you look at her credentials, she really has touched just about every major unmanned mission in the last 50 plus years. It's really remarkable. Her career began in the late 1970s. She got her degree from California State University. She started working at the Jet Propulsion Lab, and right at that time, she started working on the Voyager. She was doing, she was a part of the imaging team, designing the sequences for the flybys with Jupiter, Saturn, Uranus, and Neptune. And then in the early 1980s, while Voyager was between Saturn and Uranus, Dr. Hansen worked at the German Space Operations Center. While she was at JPL, she finished her master's and then her PhD. And then in the early 1990s, she started working on the Cassini mission. And she was part of the ultraviolet imaging team, and she still is a co-investigator for the Cassini team. She was also part of the team, if you're not going to talk about this tonight, that actually studied the water vapor plumes coming from Enceladus. And this was pretty, little work because it really helped confirm the idea that there is likely a subsurface ocean on that moon. So for her work in studying Enceladus, Dr. Hansen received the Edward Stone Award in 2007 and a NASA Exceptional Scientific Achievement Medal in 2009. She retired from JPL in 2010, but again, as I mentioned, she works at the Planetary Science Institute in Tucson, where she is the principal investigator for the high-resolution imaging science experiments on the Mars Reconnaissance Orbiter. And she's written a great book about this as well, called The Pristine Beauty of the Red Planet. But probably, at least for tonight, probably her most salient accomplishment is that she is a collaborator on the Juno mission. And she is responsible for the development and operation of the Juno camp, which is really pretty impressive. And for that, she received NASA's Outstanding Leadership Medal in 2018. So tonight, Dr. Hansen is going to talk about, or talk is entitled the Juno Camp Images of Jupiter, a New Perspective, talk about the Juno mission, and some pretty amazing photographs from the Juno camp. So Dr. Hansen, it's really a privilege to have you. Thank you.
Thank you for inviting me. I'm going to go ahead and share my screen now. And I guess I'll just mention that the only planet I haven't worked on is Venus. So anyway, let me, so once I put this in presenter mode, I won't be able to see any hands raised or anything like that. So if you have a question, just feel free to sort of holler it out, and I'll answer it right there on the spot. Okay, can everyone see this okay?
Yes.
Okay, great. These are 4 different images of Jupiter. So what I'll talk about tonight, I'll give you like the 2-second overview of Jupiter, just in case anyone forgot 3rd grade. I'll talk about the Juno mission, but the bulk of my time will be spent talking about our camera and the role of citizen scientists, and I'll give you a scenic tour of Jupiter. And as it turns out, artists have discovered us. So that's been really exciting as well. And then a little bit about our extended mission, which is going on right now. So here's the 2-second overview of third grade. Jupiter is the largest planet in the solar system. You can see they're scaled to the Earth. It's what we call a gas giant. So we are only looking at atmosphere. There is no solid surface underneath those clouds. Mostly it's composed of hydrogen and helium, but what gives the clouds their color are different compounds with sulfur and ammonia and methane and higher order organics. So that's what gives us those colors. The dark ones, the dark stripes are called the belts. The bright stripes are called the zones. And on the right-hand side, maybe you can see my cursor, that is the great red spot right there. And as far as we know, it's been there for literally hundreds of years, churning away. With no solid surface, there's no way for the atmosphere to really lose energy the way storms, when they come onto the, come onto Louisiana or wherever, they suddenly start losing energy. Not on Jupiter. Okay, so Jupiter has 4 large moons. We call these the Galilean satellites. They were discovered by Galileo, and then there was the whole business with, is the Earth going around the sun, or is the sun going around the Earth? And it got him excommunicated, but we now know the Earth goes around the sun. So it was a real paradigm changing time. And so these 4 satellites from left to right are called Io, Europa, Ganymede, and Callisto. And 3 out of the 4 are larger than our moon. And then these 3 to the right, Europa, Ganymede, and Callisto, are all covered with water ice. On Europa, that water ice boiled away long ago because of the volcanoes. And so we are just looking at rock, and in fact, a lot of molten rock. So these all have solid surfaces. Okay, that was third grade in a nutshell. Juno. Juno is in orbit around Jupiter now. And there's a couple of things that are firsts. We're the first solar-powered mission to Jupiter. My slide says 8 science instruments. I'm actually pretty sure it's 9. It's a polar orbiter, a spinning polar orbiter. So that's quite different than the types of spacecraft that we usually launch. So we launched in August of 2011. It took us 5 years to get to Jupiter. And our prime mission was 35 orbits that are 53 days long. So it was really a gorgeous launch. We all ignored the alligator prowling nearby. Anyway, the key to this mission is the fact that it's in a polar orbit. So we came in from the direction of Earth this way. We were captured into orbit around Jupiter, and then we started going into these 53-day orbits. So as you can see, we only spend a little bit of time actually close to Jupiter. Most of our time is spent, pretty far away. And then the other thing I want to point out in this diagram, where'd my cursor go? There it is, are these red ellipses around, or circles really, around Jupiter. And that's the 4 Galilean satellites. So you can see with that polar orbiter, we were never going to get anywhere close in our prime mission to any of the moons. So it's really, or at least it started out as very much a Jupiter-centric mission. And so the kinds of questions we wanted to address, does Jupiter have a core? What is the nature of its magnetic field? From the Earth, you can see its aurora. And so that was pretty cool. We wanted to learn more about that. How much water is in Jupiter's atmosphere? So those were the nature. When you start a mission, you write down, okay, what do we want to learn? Well, then you say, okay, what do we need to measure to address these questions? And then you say, all right, what should our payload be? What instruments do we need to take? Now, when all of that was said and done, there was actually no compelling need for a camera. But my boss said, we are not going to Jupiter without a camera. So because we didn't need the camera for science reasons, he said, we'll make it an outreach instrument and we will open it up to the world, literally, to participate, not just observe, not just look at a website or something, but to be a part of it. And so it was that sort of notion that drove our whole operational concept. The other thing was that we were really stuck with the leftovers. After all the big, good, important instruments had their spots, we got the leftover mass, power, volume, funding. And so the volume constraint was a big one. And I realized there was no way we were going to carry a big telescope like Cassini or like Voyager. Our camera is literally, you can't see my hands. It's about 8 inches, maybe 10 inches. And so we said, okay, well, what's unique about this mission? And let's just focus on that. We're not going to get movies. And what was really unique were the poles of Jupiter, because Jupiter's obliquity is only about 3 degrees. So from the Earth, you never see very much of the poles, not like Saturn. Saturn is tipped over like the Earth is. And so we get great views of Saturn's poles, but not Jupiter. And as it turns out, all the spacecraft that had ever gone by also were pretty much in the equatorial plane. So we said, okay, we are going to focus on the poles. And then we said, we need to get the whole pole in one image because we don't have the ability to add moving parts. And we're on a spinning spacecraft. So that in turn drove the width of the field of view. So it's a 58-degree wide field of view, which is also very unusual. So now that we had our camera designed, we said, okay, 2 of us sat down, Elsa Jensen and I sat down and said, we've worked with imaging teams our whole career. What does it take to be a member of an imaging team? And how are we going to invite the public to be part of that? So we put things in boxes, 5 as it turns out, and said, okay, these are the 5 important elements of being a member of an imaging team. Now I have to say, with hindsight, some of these did not work that well. So, but what has worked incredibly well are planning and image processing. So I'll tell you a bit about planning and then a lot about the image processing. So we invited the amateur astronomy community to join us. We said, just upload your images and with some, ancillary data. And when you click on anything on the left here, you bring up that person's image. And I have to say, some of these guys have amazing telescopes. But in any case, what we do then is we take these individual images and we string them together and make a cylindrical map. Because Jupiter is a constantly moving atmosphere, things move around. And so you can't really plan very far ahead. You want the latest, greatest notion of what's going on Jupiter to help you decide what to look at. And then we get a tremendous amount of help from the British Astronomical Association, the Jupiter division. So I don't know if you guys are familiar with these guys, but they are amazing. They collect data from all over the world. They put it together into maps, and then they label the maps, which is very helpful to me. And then you can see these 2 arrows here that pointed out, okay, on Perijove 31, Juno is going to pass across right like that. And so then we can look around and say, ooh, we're going to miss the great red spot. It's just over at the limb, but we'll get a really good view of this thing, whatever it is. So that's the planning section. And you guys are welcome to jump in and join us on that. This website at the bottom, if you just go to JunoCam, that's where all 5 options are. And then you can click on planning. This one is now going to processing. And so what we have are 3 different galleries. And the top one is raw data from JunoCam. The next one down are like our favorites, and the bottom is everything we've ever gotten from the public. So there's room. What we do is we put our data out and we say, it's our data. It's not my data. It's our data. Take what you want. Just please do us the favor of, when you process something, put it back on our website so that we all can enjoy it too. So if you click on any one of those images, what you'll find is that on the lower left, there are all of these sort of little strips, and those are in red, green, and blue. And then, so that is really raw data. So then we take those strips and we assemble them into their colors, the red, the green, and the blue. And then we stack these 3, we do a map projection, and that's what the big image is. So people can choose, and we have people that love the raw data. They go straight to the raw data. We have others who would rather start with something that's already with a mild color reconstruction and map projected. So everything in between. Okay, I'm going to stop for just a second. Are there any questions? Okay, I feel like I'm going really fast, but I have so many pictures that, and I know you're going to love them. So I'm kind of wanting to get to those. Okay, so here's the big 53-day orbit and the orbits of the Galilean moons. And as you can see, our best views from JunoCam are right in this time period. And especially like right at closest approach, we're just a couple thousand kilometers from the actual cloud tops. So it's pretty amazing. And the spacecraft is going so fast that we go from the north to the south in just 2 hours. And then, we stretch out and have our other 52.5 days of the orbit. So here's what's interesting about that 58-degree field of view. We sized it so that when we're over the north or over the south, we get the full planet in our field of view. So up here in this row, you can see there's the North Pole, and over here is the South Pole. But here in the middle, we're only just picking up this little sliver of the planet. So when you look at an image like this, or like this big storm, that storm is not that big. It's just that, we've got our eyeball literally right on top of it. So that's why it gets very distorted, but fun kind of at the same time. So it's all good. Anyway, you guys looking through your telescopes would see something on like what I have here on the left. But what we see through JunoCam is we come in from the north. So we get the half of the North Pole that's not just in darkness, because night day kind of darkness. And then we come down and we do this very high resolution sliver of images. So a lot of the images that I show you are going to be these ones that are very high resolution, but only cover a small bit of territory. And then as we leave Jupiter, we get more and more in our field of view. It overlaps more, as you can see here. And then we get the South Pole outbound. So I'm going to be showing a lot of enhanced color and a lot of exaggerated color. So I thought I should start by showing, kind of the real color. Jupiter's very pastel and it's very beautiful, but you have to look hard to see things. What I've found is that the exaggerated color really helps me to see the details in these clouds. And so that's what I wanted to show you guys. So starting at the top, I'm going to take you on a little tour of Jupiter now. And so this is the North Polar area. And one of the first things that happened was we actually discovered that there are these circumpolar cyclones. And we know they're cyclones because we had just enough time-lapse photography to get the direction of rotation. So that was JunoCam's first big discovery. And I have to say, after that, we were like, "Ah, we're a science instrument too." So here's some more, a bit more recent images. And so you can see, and this is also a good example of, this would be sort of the true color that we would post on our website. But what happens when you enhance that color, when you bring out the contrast and things like that, you can see really an awful lot more, especially along the terminator, the terminator is the division between night and day. You'll hear me say that a lot. And so, for example, this particular cyclone is almost at the North Pole. And in the north, it's surrounded by 8 of what we call these circumpolar cyclones. The other thing I want to point out is that the contributor I have listed at the bottom of each one. So these are not products coming from the non-existent JunoCam imaging team. These are really, what the public has provided and that we so appreciate. So here's a better view that shows you both. So we have to go by 2 perijoves to get both sides and not have it be in the darkness. One half is always going to be in darkness. So here's the north with this circumpolar cyclones around the central North Polar cyclone. This little guy snuck in. He's kind of annoying. He shows up all the time. And you can see the cyclone right at the pole there in the middle. And then to the left, what I have is one of our artist renditions. So what would this look like to you if you were an artist? Might look like the one on the left there. So it's been just this wonderful, wonderful camaraderie between the people doing the image processing and people. So Brian Swift did the original processing, and then Navaneeth picked it up and added the artistic flair. Okay, so moving now to a little bit away from the pole, you can still see the circumpolar cyclones right here. But we're getting into this area that we refer to as the folded filamentary region. And it's just amazingly turbulent. And you get these big globby structures that I wish someone had come up with a better name than folded filamentary region, but anyway. Here you can see them a lot better. So again, one of the northern circumpolar cyclones, but then this whole band in through here has just this amazing turbulence. And these big ones, the FFRs, rotate kind of in a cyclonic fashion, but a lot of turbulence as well. And then if you add in an artistic touch, this is one, Gerald is one of our very best contributors. He invented a way to take out the day-night shading from the terminator to the illuminated limb. So he goes in and just batch processes everything. And then Sean Dorn, who is an artist, came along and added his own color palette and his own, the way he sees things. And the amazing thing to me is that all of the structure in this image you can find back in the original, but it doesn't stand out. It doesn't look like this. So it's actually a real service, I think, that the artistic community has joined us.
Dr. Hanson,
Yes.
question. Can you go back to the previous slide? I know this is an artist representation, but I'm looking at that one right in the middle, and it looks like it has so much depth, like it would, like a tornado would have on Earth. Are we?
Yeah, I agree. I agree.
Are we looking at tornadic activity, however you say it?
Yeah, no,
I-
I wouldn't necessarily say that, but I would definitely say that there's a very three-dimensional structure to these storms. And for example, this one right here, you can see the white haze crossing over that orange red vortex below it. And probably the rotation is this way. It's hard to say because this one I only have a still, but yeah, you can definitely see the three-dimensional nature.
Thank you.
Dr. Hanson, questions?
Yes.
You said that the cyclones are stable, but I mean, are there, from the images that you've taken, are they fusing at any point together? In other words, do you have things that they come together and become a bigger one, or they go away and then appear somewhere else, or
No,
they're literally stable as they appear?
there is, well, they are stable over the last, let's call it 7 years. Because when we got to the North Pole, there were 8. And there are still 8. There's that one little interloper guy who kind of comes and goes, but the big 8 are still all there. Now they move around a little bit relative to each other, like they might bump into each other, but we've never seen one merge with another one, which is different than other areas on Jupiter. There's a different area called, it's where the string of pearl storms are. And I have some pictures of that. But in that area, these big white ovals actually bump into each other and fuse, and then other times they'll split. But at the poles, it's a very stable configuration.
Doc, with the view I'm seeing, I see eddies and currents that you would see in a stream from an underlying structure
Yeah.
that would be consistent and just changes with water flow, but it's always there.
Yeah.
So is there something that you've determined or been able to see through that layer that causes these vortices to remain stable and consistent that way?
Yeah. So on Jupiter, the winds in belts and zones are generally going in opposite directions. And in between the two, you get a lot of eddies. And those eddies might develop into big storms, or they might just stay small. And but yeah, it's the basic idea of you've got these two currents going different directions that sets it up. And actually, I'll show you guys, we have a citizen science project now to actually try to understand more about that. Here's another example, and I'll just point out, this one is similar to the other one in that you've got this kind of layer of hazy clouds that looks like it's blocking the view of the orange storm underneath. And then you've got all this orange stuff around the edges. Who knows what that is or why it's there. And also, you see these little teeny white ones. Those are ammonia ice crystals. And so I've been actually working on those a little bit. So here's another one where this one I'm not sure that I would trust all of the detail, but this is another one where the artist has come in and added their own sort of structure and made the boundaries a lot more definitive between these storms. But still just gorgeous to my mind. Okay, so now we're down to the North Equatorial Belt. So we're down to about 20 degrees north. And actually things started to get sort of fuzzy in our images. And I'm not sure if it was because we were so close or if it's just, you know, the clouds themselves are a bit hazy. But you can see going further away from the North Equatorial Belt that there's still just an amazing amount of structure and detail in these clouds. And then Jupiter has these things we refer to as hotspots. And in the ground-based data, like this is a Gemini near infrared taken at 5 microns. Anything really bright here is really hot, right? Well, we were able to map this hotspot here to this part of our image. And of course, we're looking deep. So in our image, it's dark. And these are the high clouds that surround it. So that was pretty cool that we were able to image a hot spot. Now I threw this one in just to show you guys, it's not just pretty pictures. We've got different teams of scientists who are working on things like the atmospheric circulation and mapping which way the clouds are going. And this gets back to the British Astronomical Society, and they do a lot of coordination between, there's a team of scientists in Spain that work with them, and then they get our images. And so it's this giant global activity without anybody saying you should have a giant global activity. So it just they get so excited about these images. I love that. I love when they're excited. But here's a place where you can see the different directions. Like there's a jet stream here going this direction, the S2 jet, and along the edges you can see turbulence building up. So the Great Red Spot, I have to say we were a little worried in 1995. So these are the same scale, these three. They're all taken by HST. And what happened was in 1995, the Great Red Spot was this big. And they kept on taking pictures. And next thing we knew, they were saying in 2014, they were like, the Great Red Spot's getting pretty small. And so in 2014, we had not arrived yet. We were actually quite worried it might be gone by the time we got there after 400 years. But lucky for us, it's still there. And lucky for me, our amateurs have helped out. Like if somebody asks me, how big is the Great Red Spot? I can say, well, it's bigger than the United States. And in fact, it's big enough to eat the Earth. So that's thanks to our amateurs getting involved and giving us, I don't want to say comic, but graphic illustrations that are very useful. And here's one. So this is actually true color. So the Great Red Spot, it's not really red, it's more like orange, but it really is a dramatically different color than its surroundings. It's high, it's cold. And so one of the things that we've thought about, although I don't know that we have data really to say this is the case, but if it's high and cold, that means it hasn't mixed with the other clouds in a while. And being up there unprotected, it's exposed to the Jupiter's radiation, and that could be causing the color to change. Here's a better close-up, and here we think we found the reason that it was shrinking. It looks like pieces of that orange are being pulled away and then carried off. And so these amazing kind of flakes just seem like they're being torn off the top there and then essentially lost from the Great Red Spot. Because as it turns out, the whole cavity that it's in has not really changed size. It's only the red part that has gotten smaller. So here's just a series of JunoCam images, and it is still kind of getting smaller, but not too bad. We haven't lost it yet. And then that brings me to this really amazing, and I know you guys are going to love this because you're amateur astronomers. There's an amateur astronomer in South Africa, and his name is Clyde Foster. And a couple of days before our 27th flyby, he sent us this image. He said, look, I've discovered a new spot. That little bright thing right there. And this is in his methane filter. So of course, we called it Clyde Spot. And what happened was just a few days later, we flew over it. And here it is. It's this little oval storm and sandwiched sort of in between the Great Red Spot and one of these other white ovals. And it was like, oh, that is so cute. And so here we also have a methane filter. And so we took a picture in our methane filter. We were able to figure out some things about, you know, the size and the structure. Well, its life did not stop there. We were able to catch it a few more times on other Parajoves. So Parajove 33, we were like, oh my gosh, look what happened to Clyde Spot. It's a little mini FFR now, folded filamentary region. And so you can see it's moved away from some of its compatriots. That's oval BA right there. And it looks actually quite sizable. And so when you put together all of our coverage, 27 where it was first imaged right there, and then it grew into a folded filamentary region, and then just 53 days later, it had expanded even more. And you can't really see it down here. It's off the edge. But basically, that team of scientists, mostly based in Spain, said, this is too interesting. We're going to write a paper. And so, of course, the title of the paper was Convective Storms and Closed Cyclones in Jupiter's South Temperate Belt. But we all call it the paper about Clyde Spot. So I love that. I love that story. Anyway, and this collaboration between amateurs and professionals, it's really strong in Europe, but we've kind of jumped into it as well and really enjoyed, you know, all aspects of it. So continuing our way south, this is the dolphin, as you can see. We all agree it's a dolphin. There's some differences of opinion about what's chasing it over here. A couple of dragons, some weird lizard. And of course, it's gone now because it was just an atmospheric feature, but kind of fun. And one of our contributors sent this shot. So like, if you were riding on a spacecraft and you were looking out your window, what might you take a picture of with your smartphone? The dolphin. Okay, continuing our trip south. Here are a couple of the white ovals I was talking about, where you get 8 or 9 of them at this latitude, and they will fuse and separate, but they're all always, you know, 7, 8, 9 of them at any given time. And here's a really good one where they're all lined up here. So 4 of them anyway are nicely lined up here. And then that brings us to the South Pole, where we discovered 5 circumpolar cyclones. So there's 8 in the north, there's 5 in the south, plus at both poles, there's 1 in the center, but not quite on the pole. So you can see here, this one, number 6, is not quite at the pole, but pretty close.
So Dr. Hansen,
Yes.
2 questions. One is, what kind of fluid mechanic modeling is being done on all this data? And secondly, what's driving this dynamics? How much is it due to heating from the sun versus internal heating of Jupiter?
So a lot of it up at these upper altitudes is solar driven. I mean, there is, of course, there's a lot of heat coming from the interior, but and there's a couple different models. You know, you can imagine cylinders rotating. That's one of one of my colleagues' sort of favorite. There's more radial things. We think that's actually not the case. It looks like these storm depths might go several thousand kilometers deep, which sounds like a lot until you remember that Jupiter's radius is 70,000. So it's still, you're still just looking at the skin of the planet. Another thing is there seems to be a lot of chemistry going on between the water at depth, and then you've got ammonia at altitude, and then you've got sulfur and methane sort of in between. So it's almost like there's these layers of different compositions, but they interact with each other. And so you get things like, maybe you get ammonia rain. I mean, some really oddball things that you would never think of if you weren't looking at Jupiter. We wouldn't think about methane rain here on Earth, or sulfur rain for that matter. So anyway, it's pretty, I won't say it's decided. There's some good theories, really good theories, but we're still really working on studying what's going on. Was there a second question, or was that both of them? Did I lose you guys?
Now we're.
Okay. Well, that actually brings me, that was a good lead on question, because I wanted to talk about the, we have a new citizen science project, and it's hosted by Zooniverse. So it's online, it's all on the web. And now I'm realizing I did not put the URL. Okay. So if you look on the web for Jovian Vortex Hunter, I'm positive you will find this. And my apologies for not putting the URL. We started this one not quite a year ago, and it's basically to identify vortices in the Jovian atmosphere. And so the tasks, there's two tasks. One is to say, are there any vortices in this image? And the other one is to circle it, and circle it with a color that is based on what color the vortex is. And so you can see on the left the two tasks, and then on the right is the catalog that's being built up. And then what the PI does is he takes, what the principal investigator for this project does is he takes these vortices and he maps by latitude where they are. And it's interesting because certain colors want to form at certain latitudes. So there's some very interesting connections there. And then, of course, the next step is to go into the more heavy duty math of how are they forming and why do they last however long they last, and those sorts of things, which I didn't actually put in a page on that. But anyway, it basically goes into the next step of trying to understand what's going on in the clouds. And then I wanted to just say a little bit more about this transition of science to art. On the left is the image that we post. The next one over is the one that Gerald goes in and takes out you can see there's kind of a color difference between the brighter side and the darker side. That's just because this is close to the limb and this one's close to the terminator. So Gerald takes that away. And then Sean comes in with his own favorite color palette and does his processing. The one on the right, that's an oil painting. So it's kind of gone all the way. And I think, in the early days, we were thinking about having a section that we would call art. I cannot draw the line anymore because I find that an image like this is still very useful to me as a scientist. And so I don't want to say, oh no, that's just art. It may be processing I would never do to my data, but it's still very valuable. So this is just a small sample of what we have, but this is a collection from Navaneeth of the circumpolar cyclones. For whatever reason, he really loves those. I'll a lot of people see Van Gogh. And so you can look in the night sky and you can see the great red spot behind his, whatever that dead tree was. I forget what Van Gogh called it. Here's another one with a different view of Jupiter in the background. This one that's a little haze in one of our Jupiter images. So Jupiter's in the sky in a lot of these. And then there's this is more art because it's more graphic. I would not try to do any kind of science with this, but I might frame it and put it on my wall. And this is probably one of my all-time favorites. Rita titled this Roses on Jupiter. And I just love this one. So one of these days, this one is going on my wall. So that was our tour of Jupiter, north to south, a little bit about the artist contributions. And I'm going to switch gears a bit here and talk about our extended mission. So let me pause again for a minute and see with regards to Jupiter, if there's some questions I might have missed.
Dr. Hanson, another question. As a result of some of the images that you were able to obtain with JunoCam, did it change in any way some of the objectives of Juno on subsequent orbits? You know, like let's focus instrumentation on some of these vortices or some of this cyclonic activity to understand, you know, what your images were showing that maybe was not appreciated before. Did it have any impact on the subsequent scientific objectives of the mission in future orbits?
Yeah, I would say just a little bit, not as much as you might think, because I mean, if you're trying to study the interior of Jupiter, then your magnetometer data and your gravity data, they don't care what's up on the surface. But with regards to the other remote sensing, the microwave radiometer, the near infrared radiometer, I would say, yeah. For example, the poles. I mean, none of us thought the poles would be so interesting. So that's one. And then there's this whole business of this sort of layers. That's been one that we've been working on with the other teams. And then one thing I did not mention is lightning. And up until now, we have not really contributed much to that, but the way the orbit is evolving, we will soon. And so that's another one where what we see and what they see, we're going to try to coordinate more of our observing plan.
A question, was there any images of any impacts during this period of time when Juno was close to Jupiter?
So not that we're certain of. Let me just say that the amateur astronomers watch all the time, right? And so they see impacts. I wouldn't say all the time, but they do see them. And so far, anything that they might have seen, we have not managed to image. It's either been so small it was gone already, or maybe it was in a longitude that we were not going to fly over. So far, we have not had a lot of success on that. Okay, well, I don't want to run out of time. So let me talk about our extended mission. So up here in the upper left, you can see this is where we started out, these giant 53-day orbits. But because Jupiter's oblate, what has happened is with time, apogee has been going south and perigee has been going north. And so the whole orbit has, let me do this the right direction. The whole orbit has twisted. And if you look up here, there's Io, Europa, Ganymede, and Callisto. And you can see that these bluish turquoise orbits are the beginning of the extended mission phase. And to set that off, actually, we flew by Ganymede. And so an enlargement of that, you can see down here where in the beginning, we'd come in, inbound to Perijove 1, and then we'd fly by. But with time, that little point there, it's a little hard to see, has been moving north. What's really important is that this inbound leg of the trajectory has been moving south. And so on Perijove 34, actually Perijove 34, I happened over here. So some number of hours before Perijove 34, we flew by Ganymede. And when we did, that shortened our orbit from 53 days down to 44 days. And so that happened on the 7th of June in 2021. We had a Europa flyby last year in September, so the orbit kept moving, and there's Europa. And one of the lessons is, if you ask me, when am I going to see Ganymede again? I have to tell you, well, never, because we have no control over this orbit evolution. It is what it is. And so we flew by Europa, and now coming up in December is PJ 57, and February of 2024 is PJ 58, where we'll get really close to Io. And so now I'm switching gears. This mission, which was never about the moons, suddenly became all about the moons. And so these are the JunoChem images of Ganymede. And so we came in from the dark side, the spacecraft did, and crossed the terminator and then imaged the illuminated part of Ganymede. And what's interesting about this is that we actually looked at the resolution from Voyager. It was 1 kilometer per pixel. I was there when these images came in, and in my memory, they were great images. But when we started comparing our new data, our JunoChem data, to the old data, what we found was the quality of our new images was so much better than the older ones. So sort of a little bittersweet for me, but in any case, it's such a fast flyby, and we can't turn the spacecraft and we can't turn the camera. So in the end, we really just got these 4 images of Ganymede. And here's a blow up of one of the areas. So I have to say, all these years of working with images, and still that importance of lighting is still like, you can never forget. So we were able to do some cool things with our data. We were able to get a little bit of stereo. So that big bright crater, we were actually able to get a nice profile across it. Also in the realm of stereo, this is mapping more of our data. And there you can see this giant orange spot. That's a big dome. It's 3 kilometers high. It's 475 by 700 kilometers in dimension. But when you look at it, there is no obvious surface deformation. It's just like the whole skin of of Ganymede just kind of raised up right there. And so that's really interesting. That was not a discovery because Voyager had seen it on the limb, but there was you didn't know exactly how high it was or what shape it was. So that's kind of fun. And then we identified 10 patera. So patera are things that kind of look like calderas, but we're not sure because they're so old. But they tend to be they look like calderas, but then they're cut through by some sort of tectonics. And so we found 10 more of those than we knew before. And plus they're kind of clustered. So there's one cluster on the side we imaged. There's another cluster on the other side of Ganymede. So that was kind of interesting. So what's next on Ganymede is JUICE, and that's the European mission that just launched April 14th. So they're on their way now. They're going to study Ganymede. That's their primary target. They will go into orbit in July of 2031. And initially, for the first 3 years or so, they will be orbiting Jupiter and studying the whole system. But then in December of 2034, JUICE will go into orbit around Ganymede. So it's a very ambitious mission for the Europeans. And we wish them the best because it's very exciting. Back to Juno. Our close Europa flyby was last September. Again, we came in from the dark side and then imaged once we got across the terminator. So by the time we got there, we were already up to over 1,500 kilometers. Once again, we acquired 4 images, red, green, blue, and you can see all of the detail that we saw in our images. And a lot of that terrain was really well imaged by Galileo, but they're big splotches where they actually did not have a lot of good data. And so we were able to fill that all in. So we'll be able to complete a lot of the structural assessments with these lineae, where do they connect and that kind of thing. And then our images along the terminator, you know, you can study those forever and a day. There's a new trench right there, bunch of pits, some really very smooth terrain here. And so we're really having fun with this data set. Nope, sorry, yes, question?
Nope.
Okay. So looking ahead for Europa, what makes Europa so interesting? As I said, it's mostly a rocky body, but we're fairly certain, I'd say we are certain, that there's a layer of liquid water and that's just covered by a thin layer of ice. And we don't know how thick the ice layer is, but we think it's not terribly thick because the surface age is very young. And so when you have liquid water and you've got chemistry and energy, the question becomes one of habitability. Could something be alive so not like Mars, where we're just kind of looking for old scum. We're asking questions here like, could there be fish? So it's quite a different situation. And so the Europa Clipper was approved in 2015, and we're at the point now where the spacecraft is mostly built, and we're at the stage where the instruments are being integrated. And I would say probably half, maybe 2/3 of them are already on the spacecraft and hooked up and being tested. We launched Europa Clipper in 2024, but we're on a faster trajectory. So we also get to the Jupiter system about the same time as JUICE. So that's going to be really interesting, having 2 different spacecraft with 2 different main, I mean, this one's focused on Europa, that one's focused on Ganymede, but we'll be able to do a lot of really comparative studies as well. So just looking ahead to Io, we are here in the purple. We are working our way in, and we're in some sort of a resonance because we get pictures of Io every other perijove pass. And you can see from the numbers here that we're working our way closer and closer. Perijove 51 is day after tomorrow. So that's going to be a really close one. And then, as you can see, we're looking at the anti-Jovian side. But once we flip around here, then we'll be looking back at the subjovian side. And of course, Io being volcanic the way it is, it's very exciting to, look forward to studying its interior. So here are just the 4, what we have so far. And you can see every pass, the resolution gets better and it's a little easier to identify the surface features. And so we're just really loving our lives right now. And I'm going to end right here to point out that we've already made 50 close passes and gotten great data on every single one.
So Dr. Hansen, on Io, are you able to hear me?
Yes.
Are you going to be are you be able to get any chemistry of what's actually being, the eruptions are actually putting out?
We hope so. We hope so. Our near infrared spectrometer is a little sensitive to all the radiation noise. So we're a little worried, but if it works well, we will definitely have some good spectra.
That'd be awesome.
Yeah.
I have a
Thank you.
question, Dr. Hanson. When you were designing a camera for this mission, it seemed to me like you had some impossible parameters to work with. The spacecraft is going very, very fast. You're dealing with a very, very big bright object. How do you decide what pixel size, what pixel depth, whether you want to use a Dyer array or whether you want to use filters, how well these hold up to the Jovian radiation belts? I mean, how did you design this thing?
Yeah, I mean, those are all such important factors. Put a camera on a spinning spacecraft. Okay, you're already in trouble, right? And
without visualization, how do you?
so basically, I knew that Malin Space Sciences built push frame imagers. And so basically, I told my boss, Scott Bolton, I said, Scott, we've got to go to Malin and see if we can get one of his cameras, because that's the only thing that's going to work out here. So what we do is, rather than fighting the spin, we use it to do what we call time delayed integration. So the photons are clocked opposite of the spin so that you're always building up signal as you're rotating. So that was the first thing. And then we had signal to noise ratio. I'll call them requirements, with the very gentle requirements, where we had to figure out, how many photons before we would saturate, or how many photons we needed to collect in order to get a signal. So there was a whole sort of calculation on those things. And then the field of view, the fact that it's 58 degrees, that was because of wanting to take pictures of the pole. But if you take what was sort of a standard CCD, and like I said, we were also very constrained on our funding, so we weren't going to be developing a new detector or anything like that. So a good match was a 1600 pixel CCD and across 58 degrees field of view. So I'll be honest, I wasn't sure it was all going to work until we got our images of the Earth. And then once we got that first image of the Earth, it was like, oh yeah, this is going to be fine. We're going to get good pictures.
I have a question. The changing orbit of Juno.
Yeah.
Seems like pain. How much more time will it be time to Jupiter?
Okay. I think I missed a little bit of that, but I think you're asking how much longer the mission will go, given that the orbit continues to evolve.
That's my question.
Okay. So the orbit is continuing to move so that the apogee is headed south, perigee is headed north. And once we fly by Io, our one orbit will be 33 days. At that point, we actually do have to go back to NASA, and we'll have to write another proposal and say, okay, here's what we can do now. But we're not positive we're going to make it to that point, because the spacecraft is flying through so much more radiation now than before, than in the beginning. I have to say, every time we do a successful perigee pass now, we're all like, whew, thank goodness, another one behind us, because it really is starting to get a bit dicey. And that includes the camera. We had a problem with the camera on perigee 46, only lasted about 11 minutes, right at power on. We didn't think too much of it other than to sort of point it out to each other and go, that's odd. On perigee 47, that anomalous time period lasted 43 minutes, where it was just right at power on. It was basically overheating. Then it reset itself and everything was fine. So we said, okay, before that, we were turning on and off at every perigee. So at that point, we said, okay, project, here's your paperwork, and we want you to next time turn us on and don't turn us off. And so, so perigee 48, they turn us on, and we were in that anomalous state for 23 hours. I mean, my team, I don't think slept a wink for 23 hours till finally The camera sorted itself out. We still don't know the cause. We still don't know how it's fixing itself, but it's been fine ever since, and we haven't turned it off. So we're in part of the gang just going, ooh, hope we make it.
Dr. Hansen, hi, I a quick question with the approach towards IO, is it flying through, I think they call it the flux tube?
Yeah, so there's flux tubes connect the satellites to Jupiter, and depending on our trajectory, we have been flying through flux tubes ever since the beginning. And it's very interesting because when that happens, you can see how the moon itself is affecting Jupiter and the Jovian radiation environment. So, and then when we get actually to Io, we'll be able to study the space right around Io while knowing what it's been doing over at the Jupiter end, and making that kind of connection. So yeah, studying Jupiter as a system is actually pretty interesting.
Okay, thank you.
Doc, can you explain the flux tube? It's just not a term I heard.
Well, as I understand it, Io, rotates around Jupiter in this space that they call the torus, and that's another affected area with increased radiation, correct, Dr. Hansen? But then
Well,
also
that's
in poles, you have this other thing going on too. I don't know how to
right.
describe
So
it.
let me separate it into two things. One is Jupiter. Jupiter has a magnetic field. So if you just think of it like a big dipole, it's not really, but if you think of it that way, you've got these shells of the magnetic field of Jupiter, and that's what we call them. We call them shells. But if you connect like a line from the North Pole to the South Pole of Jupiter, that would be what we would call a flux tube. And if your moon passes through the flux tube, then it's, a connected flux tube. But what you're talking about, the torus, is a little different because that is in Io's orbit, and it's caused by the fact that Io has volcanoes. So it's always spewing out gases and particulates and lots of gases. And then the gases almost immediately get ionized because they're in the Jovian magnetosphere. And then those are free to start going back and forth on the flux lines. So they're kind of connected, but they're in two different planes, so to speak.
Thank you.
It's kind of like, I don't know why I always think this way, but it's like a cake pan cover with the handle. I don't
You
know.
can probably think of it that way, yeah.
You probably never heard that analogy before, that's for sure. Okay, I'm going to shut up now.
Any other questions for Dr. Hansen? Dr. Hansen, thank you again so much. Good job.
You're very welcome. Very, very welcome. So I'm going to leave now. I've got to go feed my dogs. See you later.
Thank you very much. What can I say? Wow.
Yes.
What images?
Yeah.
And it's really cool to see what the amateurs are bringing to the table. The history of astronomy is replete with amateurs stepping up to the plate and, contributing. And this is just another case of it. And it's like, hey, maybe we matter for something. So Bruce, fantastic job all year, which has some incredible speakers and some great programs. I can't wait to see what we're going to have come September. Do you want to give us a quick overview? Just brief.
Yeah, so we're going to have a talk by John Conrad in September on the OSIRIS-REx mission. It'll be very appropriate timing because it's returning. In October, gonna have a talk from an astronomer in the Lehigh Valley Astronomical Society. He's gonna talk about origins of the constellations, how they were named, how they were discovered, kind of a historical overview. In November, we have an author, an astrophysicist, and this is gonna be kind of a little wiggy bit of a topic. She wrote a book about the ethics and the politics of living in outer space and what, you know, what that could mean. And it's a really good book. And Don Miller and I bought it, and I emailed her, and she's going to give us a talk about that. Wow. And then in December and January, Don is going, he's off now. Yeah, no, he's still on. He's going to be giving a pair of presentations that he has prepared. I'm not going to mention what they're about, but they'll match one another. So we'll have one in January and one in February. So nice, diverse range of topics. And that's why I was saying, everyone, please let me know what else you want in the spring, and I will hunt people down.
And also, as a former program chair, I'd like to put it out to any of the new people or any prospective members. We welcome any member of the club that wants to present a topic. And we don't care what it is. We don't care if it's you're building your new observatory, whether it's a particular subject that's near and dear to you, whether it's actually some work that you've done. You know, this is your club, and this is your space to be able to present and share with the rest of the group what you're doing or what you're up to. And trust me, we will be there. We'll be looking, we'll be every bit as interested. So if you have something that, even if you think you might want to talk about, let Bruce or myself know, and we'll get you on the docket. So think about that, please. Again, it's a fantastic academic year, great programs, incredible subjects, some of them just mind blowing. And hey, let's get out there under the stars now that the weather's warm. And we'll see at BRC, or if you're not up to going out and seeing the stars in the sky, we'll definitely see everybody back here in September. Looking forward to it. Have a great summer.